Good afternoon. My name is Roger Jones. Today we're going to be talking about vacuum heat treating of additive manufacturing components. A brief synopsis concerning myself. I've been involved with the heat treating industry since 1975. I worked with Solar Atmosphere since its founding in 1983. At that time, our company joined MTI in 1983, and I became an MTI board member and served on the board from 1998 to 2012. I was president of the MTI from 2004 to 2005. Also, my service with ASM International, I was president of the ASM Heat Treat Society in 2013 to 2015, as well as I served on the ASM Board of Trustees from 2015 to 2019, and I became an ASM Fellow in 2018. Transforming technologies that have changed the world. Back in the 1870s, the light bulb was Edison's transforming technology. Today's transforming technology is additive manufacturing. What is additive manufacturing? Additive manufacturing is a process where a digital model is converted into a component layer by layer versus subtracting material from a larger piece of material as in machining. This particular picture shows some Inconel 718 cooling chambers which cannot be made conventionally or by brazing. So let's talk about the variety of additive manufacturing processes that are available. First, we have the powder feed technology, which is a powder bed fusion. We use selective laser melting, or SLM, direct metal laser sintering, or DMLS, electron beam melting, which is EBAM, direct energy deposition, which is DED, laser metal deposition, LMD, laser engineered net shaping, or LENS, and of course the binder jet process, which is a polymer ink process, and lastly the fused deposition modeling FDM polymer metal hybrid. So the wire feed process, which is a laser metal deposition and is also utilizing electron beam additive manufacturing, or EBAM. The laser metal deposition is used by wire, basically. So the three major processes that we're going to cover today are the direct metal laser sintering, or DMLS, electron beam additive manufacturing, or EBAM, and lastly the binder jet process, BJP. So let's talk about direct metal laser sintering. First, we have a 3D model that's on the computer screen. We have a layer of powdered metal material that is applied to building a platform. The powdered material is solidified into a cross-section of a model with a laser, as you see. Then the building platform is lowered. The next layer of the powder is applied, and the process repeats itself until the part is complete. It's very important that the unused powder is removed prior to the finished part going for heat treat. We have direct metal laser sintering. Instead of a powder bed, the powder flows into a laser beam itself and gets melted onto the platform, and the platform moves back and forth. This is a newer technology that is out there. So here's a picture of a direct metal laser sintering, DMSL. This is done within an inert chamber. A focused laser melts the surface of the target material, forming a pool of molten metal. The metal powder is delivered onto the molten pool, forming a deposit. This particular part in the picture that you're looking at is a piece of titanium 6Al4V. This is printed hollow. It's roughly 4 feet tall, and this was actually used as a decorative piece for a yacht. So another picture here. This is another picture of direct metal laser sintering. This process has a low rate of deposition, however, it results in a finer, detailed product. The material were used with this method are titanium, Inconel, cobalt chrome alloys. This particular part that you're looking at is a piece of Inconel 718 that was orbital welded. Now it's printed as one piece via this process, which would be 50 parts versus one piece. This is an oil and gas packer. Electron beam additive manufacturing, or the EBAM process, is done with electron beam gun. The electron beam points down and onto the molten alloy puddle, and then it deposits the substrate, which then creates the part, moving back and forth. So as we make these parts, The electron beam additive manufacturing is done within an inert chamber. It's a multi-kilowatt electron beam and is used to selectively fuse wire onto a backer plate, similar material. Multiple layers of wire are deposited, forming the rough shape. The process has a high rate of deposit, forming a less detailed part. What you're looking at here is some parts that have been completed. These are titanium 6Al4V. This was done by the Siaki process, made to near net shape. As these parts get processed, the most common materials we work with is titanium 6Al4V. However, the backer plates warps, and vacuum stress relieving is required, and creep flattening is required. Here in this picture, you see the part which is heavily laden with weights on graphite plates. This is taken up in a vacuum furnace to relieve the flattening, the creep, and get it as flat product as possible. Here's an example of Arconic's Ampliforge process. This is actually an added twist form EBAM to near net shape. These parts are roughly on the left about 4 feet tall. The parts to the right are much smaller examples of the same process. So let's talk about the vacuum heat treating of parts using the binder jet process. This is a liquid binder that's sprayed onto a bed of powder at ambient temperature. So the binder is then solidified by a low heat source similar to a heat lamp. After each layer solidifies, the platform lowers until the 3D part is complete. The reason I'm showing this picture is sintering of these parts is very, very critical. You'll see the inside of a vacuum furnace with the type S thermocouple merely an inch or so from the part. The sintering temperature of this particular part is 2436 degrees Fahrenheit, plus or minus 2 degrees. So a temperature measurement is very important. Temperature is just like when we do it in the MIM process. Dimension controls are tight. This particular part is a Inconel 625 piece that's being heat treated. Okay, during the binder jet process, this is the 3 of the lowest cost methods that we're discussing. Deposition is slow, however, details of the part can be fine. The most common materials that are processed are titanium and nickel-based alloys. In this picture, you see titanium dog bones for mechanical property testing, which is very important. Also, these binders can hurt the vacuum furnace. However, over the years, there have been improved binders and are starting to work well within vacuum furnace processing. Okay, so some of the benefits of additive manufacturing components. First, there's less input material required to equal less waste. There are 0 design constraints. It's fast and efficient prototype development. Reduction of supply chain constraints, so the designs move around the world as digital files, not as products. Reduced inventory levels, opportunity to reshore current foreign production, and lastly, significant reduction in the carbon footprint. Let's talk about considerations of additive manufacturing components. First, the high cost of printing machines and feedstock material. Most require spherical powders which are atomized. There's industry-wide standards which are limited. New quality and certification standards are also needed. Slow build rates are not conducive to high production. Component size restricted by printer dimensions is also to be considered. Printers are not calibrated and operator training needs to be improved. Powder safety considerations also with handling and storage of these materials. Challenges with powder and wire heat lot integrity is also important. So, why do we vacuum heat treat? Post-processing is dependent on final properties and microstructure required for ultimate lifetime of the part. High residual stress from rapid cooling of the melt pool as layers build, which is for stress relieving of those particular parts. Very fine microstructure from rapid cooling of layers, so we have to anneal. Process may cause segregation of alloying elements, so solution treating and aging. Also, in the binder jet process, vacuum sintering is the final step, which is also important. Mechanical testing is also very critical. An amorphous structure which has no longitudinal or transversal grain orientation, so having these test bars as in every load is very critical to the final part. So controlling the energy is the holy grail of additive manufacturing. This particular slide shows a piece of Inconel that's 2 inches by 4 inches, By controlling the energy, they're able to actually flip the grain orientations to spell DOE, or Department of Energy. This was built for design by the Department of the Energy. So, additive manufacturing is made for the vacuum furnace as well. Additive manufacturing surfaces are near net shape, creating zero tolerance for surface contamination. As stated before, temperature control is very critical, plus or minus 2 degrees Fahrenheit in many instances. Additive manufacturing sintering temperatures can reach as high as 2,500 degrees Fahrenheit. Vacuum furnace technology allows for direct thermocouple placement. Also, hydrogen partial pressure in the binder jet process can be used to improve mechanical properties of certain additive manufacturing parts. So let's talk about additive manufacturing in the vacuum furnace. Slow ramp rates with lower intermediate holds are utilized to evaporate residual binders after the delobe or post-printing of the BJM process. Graphite fixturing and crucibles are needed for additive manufacturing parts and can only be used in the vacuum furnace. And additive manufacturing components require vacuum levels of 10 to the minus 5 to 10 to the minus 6 torr range. This particular picture shows some 300 series stainless steel parts. Note where the thermocouples are in the parts and not in the base plate. So measurement of the part temperature is very crucial. Okay, here's a picture of titanium manifolds. And it's very important when you have these intricate parts that the fine powder is removed prior to processing, or it's going to cause problems down the road. Here's another picture of some parts inside the vacuum furnace. Note that the thermocouples are on the base plates for temperature control. The Inconel thermocouples come through the bottom left-hand side of the furnace and then into the jack panel on the right-hand side. Okay, some lessons that have been learned during the process. First, we have to avoid alloys that require liquid quenching due to potential distortion. All printed internal cavities must be vented to avoid binder powder blowout. The build plate thickness must be equal and printed component to the component thickness. And then printed thermocouple hole design is also crucial. On the picture on the right, you see a base plate where the part had cracked, and also the thermocouple holes on the other picture showing thermocouple placement in the part for temperature measurement. So some other lessons learned. This is some DMLS parts that need to be thoroughly free of residual powder. All the printed bind holes and cavities must be completely blown out prior to vacuum processing. Failure to do this can result in extremely costly hot zone replacement. In this picture, you can see where some of the powder has blown out of the part and has been deposited on the moly heating elements as well as the moly metal in the backing. And because of this, this hot zone had to be pulled apart and cleaned. So it's very important that these holes are free of any binder and powder prior to processing. So is additive manufacturing going to change our heat treating industry? Some early adopters were the aerospace market. This is a GE fuel nozzle for the LEAP engine. Before, this was brazed in 6 components together. Now this is printed as one part. 18 pieces in each engine. So as you can see, this gets a lot of parts in the engine. It also is lighter and more fuel efficient and saves billions of dollars of fuel, and cost is no object to save fuel at this point in time. Also below is a picture of a medical device implants. The same thing. We're seeing more and more medical parts made in this process. Some more early adopters. The first FAA certified structural additive manufactured part made of titanium 6Al4B. Note these parts were produced by Norsk Titanium, and these are destined for installation in a Boeing 787 Dreamliner. These are in fuselage parts. So is additive manufacturing going to change our heat treating industry? Let's look at some facts. Nearly all prime, first tier, and component suppliers in the aerospace industry are driving additive manufacturing parts into their new aircraft designs. Additive manufactured parts are already flying on commercial aircraft, and more are being added daily as additive manufacturing technology becomes more widespread throughout the original manufacturing and MRO activities, and as quickly as AM parts can be qualified for new and existing requirements. Some other facts. SAE, Additive Manufacturing Committee, held their first meeting in July of 2015. The goal of the committee is to generate aerospace industry specifications for additive manufacturing. Also, ASTM and industry partners established the AM Center for Excellence, COE, based at Auburn University in 2017. Part of this effort includes the advancement of additive manufacturing through standardization, which is ASTM Committee F42. So, some other facts. Currently, there are 177 3D industrial system manufacturers around the world, an increase of over 31%, which is year over year. In 2018 alone, over 19,000 industrial 3D printers were sold. In 2017, additive manufacturing grew 21%, and the market spend was over $7.3 billion. Also, additive manufacturing industry grew more than $1 billion annually for the third consecutive year. As you see in the footnotes below, a lot of this information came from the WARS report 2018 and 2019. Some more predictions. Less raw materials and more near net parts will be heat treated. There will be also changes to brazing services. Hipping will become more prevalent. Thermal spray and case hardening processes may become unnecessary as the ability to print substrate layers is developed. Vacuum furnaces will outpace atmospheric furnaces. Also, we should note that certain alloys, all metal hot zones, and vacuum furnaces are required for processing additive manufacturing parts, particularly titanium. Also, certain microstructures may be obtainable without conventional heat treat due to rapid cooling and power control capabilities of additive manufacturing. Wanted to make note that in a HIP furnace, parts are heated at a high temperature and are cooled slowly. However, with a vacuum furnace and high pressure gas quenching, it's a key benefit to vacuum heat treating, as you can quench at significantly higher pressures and quicker velocities to get full metallurgical structures as quenched. So today's heat treat customer is a lathe, as you can see here, that's spitting out metal chips day after day. This is what we're currently seeing. And tomorrow's heat treating customer is actually happening now, with rows and rows of 3D printing machines printing parts that have to be heat treated. So, is additive manufacturing going to change our heat treating industry? The pessimist complains about the wind, the optimist predicts it to change, and the realist adjusts its sails. This was a quote from William A. Ward. I thank you for your time today. I would look forward to your questions in the chat room. Thank you very much.